But you're giving my video proof that there's people in this class, which is good. Okay, so here we go. Part 2. Let's see. We're going to start with arc lengths. Okay, so let's talk about arc lengths here. So from prior, we talked about how an angle in radians could be the arc length over its radius. Okay, and then if you solve for the arc length s, you get arc length is equal to the radius times the angle. Okay, so that was just a little recap from yesterday. So this formula is to find the arc length. Okay, and what's important is theta has to be in radians for this to work. It can't be in degrees. Okay, you can't have like meters and degrees. Like it just doesn't units don't mesh well. That's why we use radians, because it's unitless. Okay, so for this example, find the length of an arc made by an angle of 225 degrees on a circle with a radius of 7 centimeters. Okay, so that's what we're going to do for this one. And we have the majority of the information, which is really nice. Reading the problem, though, this is in degrees. Okay, so I can't use this formula if it's in degrees. So I got to do a little conversion. Okay, so let's do that first. So my theta, my angle, is 225. So let's do a little bit of a conversion here. So 225 times, it'd be pi over 180 to convert that into radians. I made the note yesterday, like you can use like 2 pi over 360. You can use any of those measurements we talked about yesterday, but this is the easiest to work with. So we get 225 pi over 180. And then you do want to reduce the fraction if possible. That makes it easier to work with those values. So we get 5 pi over 4. So we're going to use that in our calculation. Okay. So over here, we have the arc lengths equal to, the radius is 7. So it'll be 7 times 5 pi over 4. Okay. Now here's what I'm going to do. I'm going to write this in 2 different ways. Okay. So I'm going to write it, leaving it as an exact answer, like in terms of pi. And then I'll use it as a rounding value as well. So if I multiply these together, do a little division, I get 8.75. Okay, pi, and it'd be in centimeters, because that's what our radius is in. So that's more of an exact answer. Let me just put that over here. So this is exact. Because if I multiply that by pi, it goes on forever, then we have to start rounding things. And if I have to use that in another calculation, that makes that even further off. So it's just easier to work with exact values. But if you were asked to come up with an approximation, we could type in the calculator. You get 27.5 centimeters. So this is our rounded answer. Okay. Alrighty. Any questions on arc lengths? Yes?
Is there a reason we didn't leave 8.7 pi centimeters as 35 pi over 4 centimeters?
You can. The only reason why I actually wrote as decimals is because it came out to be an exact decimal.
Okay.
But yeah, you
Okay.
that's the only reason why. If I had a fraction that didn't give me an exact answer, I'd leave it as the fraction.
All right.
Good question. Okay, let's talk about latitude and longitude. So latitude is the number of degrees north and south of the equator longitude of a point is the number of degrees east or west of, like I'm stepping on something, I am stepping on something. The Greenwich Meridian. By the way, this is in England, where we decide. Okay. the point would be our 0 degrees. Okay. So latitude and longitude. Okay. And I mean, you've seen latitude and longitude in the past in your prior classes, so we're going to use that in our next example here. The good news is in our examples, if we're like trying to figure out the distance between two cities, one of these, latitude and longitude, one of them is going to line up pretty nicely to where there's only a difference between one of them. Okay. We haven't got to the point yet in this class where we can talk about differences in both of those. So let's give it a shot. Okay. So we have the cities. And I'm going to butcher their names, and I'm going to feel bad for this. So I would say Quito, right? I think that's Q-U-I-T-O. Quito. Yeah, that sounds a little better. Ecuador. Macapa. Maybe. We'll say that's in Brazil. Both lie very near the equator. So that would be at a latitude of 0 degrees. Okay. However, Quito is, well, that's not, let's try rewriting that again. Is approximately 78 degrees west longitude. Wow. Kappa is 51 degrees west longitude. So I'm going to stop there for a moment. So because they're near the equator, we're pretty much assuming that they're north and south of each other. So we don't have to worry about them varying. So we're only going to worry about the east and west side between these two cities. Assuming the Earth has a radius of 3,960 miles, how far apart are these cities? Okay, so that's what we're going to try and figure out here. By the way, there are some problems that you're going to see, and the textbook does it too, where they'll actually give you the latitude, both degree measurements, and you're going to see that they're roughly the same, so you can negate those and just focus on the other measurements and using those to find how far apart are those two cities. So just as a visual, I mean, kind of like what we're doing here. So we have one city up here, one city down here. That's not a star. That's a star. And we're going to find the distance between them on the globe here. Okay, so this is what we're trying to find. Okay. So first off, I got to figure out the angle, right? So if I'm going to find the arc length here, which is r times theta, I need to know what the angle is. So what I'm going to do is subtract the two angles that we have here, 78 degrees west longitude and 51 degrees west longitude. Okay? So let's do that. So we get 78 minus 51. Give me 27 degrees. Now to use that formula, just like over here, I have to have it in radians. So let's convert that to radians. So we're going to get 27 degrees times pi over 180. Okay, we get 0.15 pi. And that's what I'm going to use for my calculation. So back over here. So my radius is 3,960. And then we're going to times up by my angle, which is 0.15 pi. And again, I'm going to do the same thing as the prior example. I'm going to give you an exact answer without rounding and then give you a rounded answer. So the exact answer, when you multiply these together, would be 954 pi miles. Okay. Again, just leaving pi just hanging out there. So that's our exact answer. Rounded answer, it's going to be approximately, let's see, 1,866 miles apart. So there's a rounded answer for that guy. Okay. All right, so that's latitude and longitude problems. Again, you're going to have at least one of those be roughly together, so you're not messing with two sets of degree measurements that are different there. Okay. Now, let's continue. So let's take a look at angles when it comes to angular and linear speed. Okay, so that's what we're going to do next now. So like how fast is an angle turning? Essentially is what we're looking at. And what would it be in terms of linear speed for that angle? So from the past, we know that the distance that something is to anything is how fast you're going, which is r, multiplied by how fast it took you to get there, so your time. Okay, we're going to apply this exact same concept to angles. Okay, so if I want to know how fast I'm going, to solve for r, I'll just divide by t. So my rate, the speed that I'm going with, is going to be my distance over time. Okay. So using this, let's talk about angular velocity. And I'm going to put a little box here because this is the one I'm going to be focusing on. So I'm going to swap some variables out. Okay. So angular velocity is the rate of rotation per unit of time. Okay. So we use the symbol, okay, this is called omega. It's a W. I try to curve it a little bit more so it doesn't look like a straight W. We're going to use that symbol to talk about angular velocity here. So we're going to use that to represent the rate of rotation and theta represent, the angle through which the terminal side has moved, measured in radians. So we're not going to use degrees for this. Okay? So we're going to use this new symbol. That's going to represent how fast you're rotating with that angle. Okay. So let me rewrite it. So we started off with the rate is distance over time. Let's just go ahead and swap out some variables. So my rate now is going to be omega. That's my angle velocity. Okay. My distance is going to be that angle. Okay, how far we went with the angle itself over time. Okay. So think of a bicycle. Okay. Think about how fast a bicycle's moving. Okay, that angle as it's going around the wheel. So how many revolutions per minute, or how many revolutions per second, whatever it is. Okay. Now, this is one formula we're going to be using. Okay, we do have another one. So we have angular velocity. We also have what's called linear velocity, right? So how fast is it going linearly? So I'm going to put that right underneath it. Okay. So again, using our formula, so R equals d over t. We're going to swap out some things. So our rate is how fast we're going now, so we're going to change to velocity. My distance is the arc length, how fast am I going across the arc, over time. Okay. Now, what's nice about this formula is we can manipulate just a little bit. So over here, I talked about how arc length is equal to the radius times theta. So let me just go ahead and rewrite this now. So the velocity, how fast I'm going across that arc, is going to be, let me swap out s for radius times the angle, theta, over time. And then I can make one more substitution, and then we'll get to the actual formula for it. Notice that theta over time is this guy, it's omega. So what I could do is I could substitute this into here to get my final linear velocity formula. So it's just going to be your radius times your angular velocity. That'll tell you how fast you're going linearly across that arc there. So those are going to be our two formulas, linear velocity and angular velocity. So we're going to use that in our next example. Okay. So let me just pause there for a moment. Anything up to this point? Any questions? Anything at all? So far, so good? Yeah, absolutely.
On the example about longitude, why did you subtract the degree amounts?
Well, I want to figure out, because put it this way, as I'm measuring like how many degrees it takes to get to the first city, right? Which is like 78 degrees. And how many degrees it takes to get to the second city. But I want to find the degrees between the two cities. So I have to subtract the two to find that angle that's between the two cities there. So I had to subtract them. Okay. We're not going to have a situation where you have to add degrees like to go from there, because you're always finding stuff between two values or two objects. Good question. Anything else? Doing good? Okay. Let's try these formulas out. So we have here that the wheels on a racing bicycle have a radius of 13 inches. How fast is the cyclist traveling in miles per hour if the wheels are turning 150 revolutions per minute? Okay. So that's what we're going to try and figure out here. So how fast is the cyclist moving? What's that linear speed going here? Okay, two formulas over there. So I'm using the second one here. Okay, so my linear velocity is going to be my radius of the wheels, which, hey, I have that part. Perfect. But I also need the angular velocity. Don't quite have that. I have it and I don't. So right here, this is how fast the wheels are turning. That's my angular velocity. But I want things in miles per hour, right? Okay, so I got to figure out that. I also want this in radians. So there's two things I got to start thinking about here. So this guy's a troublemaker. I got to work with that a little bit. So we know that this formula, the angle that we're going with over time. So this whole thing, the problem tells us it's 150 revolutions per minute. Okay, so the problem did give us the angular velocity, which is awesome. But I do want to do a little conversion. Okay, I want to convert this into some radian measurements, and then I can plug it into here to finish it. So let's do that. So we know that one revolution, because we're talking about a wheel here, is going to be 2 pi radians, okay, for one revolution here, for one turn of that whole entire wheel. So if I multiply those together, I get 300 pi, okay, and notice that the revolutions cancel out, which is perfect. That's what I want. I want to put this in radians. And then we are left with just 1 minute, or per per minute. So we're going 300 pi radians per minute. That's your angular velocity, which is pretty fast. Okay, now we can plug it into here. So the radius of the wheel is 13. And then we already found our angular velocity. So it's 300 pi per minute. Now I know already, and we'll get to it, but they want miles per hour. We'll get to that. Okay. So this comes out to be 12,252.2. Okay. And this is going to be in inches per minute. Okay. Now, little conversions, right? Because we want, again, miles per hour. So how do we convert this? Well, let's do it down here. So inches per minute. Okay. If you've done, anybody in chemistry or done chemistry? You've done conversions, right? You've done a lot of conversions in chemistry. It's kind of following the same pattern here.
Too many.
Okay. So we have, there are 60 minutes in 1 hour. So that's me just converting the minutes to hours there. And notice that the minutes are going to cancel out there for unit-wise. Now I got to figure out how to convert inches to miles. Okay, so in 1 mile, there is 63,360 inches. Okay, so now the inches we're going to cancel out unit-wise. I'm left with miles. So I got miles per hour now. So multiply straight across, and same thing in the denominator. Divide those, we get 11.6 miles per hour. That's how fast he's going on the bike. Okay. Alrighty. Just about done, but any questions on that one? We gotta just do area of a sector, or area of a sector of a circle, I meant to say. To finish it up. I do apologize, this one's a little bit of a lengthier lesson. It's just creating a foundation for us that we're going to be using throughout the future here. Okay, so let's talk about computing the area of a sector of a circle. And honestly, this one, besides the whole radian stuff, it should sound familiar from geometry because you did area of a sector in geometry before. So here's what we do know. Okay, so let's say I just draw a little picture here. And here's my center. And I only want that chunk of the circle. Okay, so this is my sector. I only want this area. That's all I want. So how do I figure that out? Well, think about something for a moment. The full area is pi r squared, right? That's area of a circle. Okay, so pi r squared, that's the full circle. Okay, and I want the area of the full circle. I only want that chunk of it. So I gotta find the fractional component of that. Well, that's actually pretty simple. If I know what the angle is, I can figure out the fractional component of that sector here. Okay, so we can take our angle out of the whole entire part, which is 2 pi. Okay. So if we multiply these straight across, we get pi r squared theta over 2 pi, which gives me half r squared theta. So this, and again, theta is in radians, okay? This is how we find area of a sector of a circle. Okay, so we got the full circle. This little fraction part is what we want. Multiply them together, and that's the area that we're going to be using here. Okay, so let's give it a shot. So the last example. What is the area of a circular sector formed by a central mean, if you want to, you could draw a picture. It's no big deal. I mean, you're just drawing a circle with a chunk taken out of it. Good news is, if we look at the formula here, it has to be in radians. It's in radians, so I don't have to do any conversion. And I need the radius, which I have. So literally, we're just going to plug those numbers in and just simplify. Okay, so area of the sector is half r squared theta. So area is going to be a half. Okay, radius is 72 squared. And then theta, which would be 3 pi over 4. That would be my angle for it. Okay. And for this one, we'll round to the 10th place. Just make it a little bit different here. So multiply all those together, and we get, so for the exact answer, it would be 1,944 pi square feet. And then for the rounded, like I said, we're going to do 10th place. It's approximately 6,107.3 square feet. Okay. And there we go. Now, once again, if this was in degrees, you got to do a little conversion first, and then plug it back in your formula, and you'd be good to go. All right, that's it. That is angles. Like I said, we need to know what angles are before we talk about actual trig stuff. Any final questions? I think we're good.